Hello and welcome back. In this example, we're going to finish the work that we started in packet 22. In packet 22, we tried to approximate the area under a curve using rectangles. We only used 4 subintervals in those notes. So we only had 4 rectangles, and the approximation was okay, but it wasn't really that great. But here, in this example, we're not just going to use 4, we're not just going to use 10, which would be in a better approximation. We're not just going to use 100, we're going to use n in general, where n is a number that we can play around with. We can let n be 1,000,000 or 1,000,000,000,000, and we're going to come up with a formula first that calculates the area under the curve using n rectangles. Then we're going to take the limit as n approaches infinity to see where the true area under the curve is approaching. Let's check it out. So example 2 says, let's write a formula for the estimation of the area under the curve x squared from x equals 0 to x equals 1 using n rectangles, and here we're going to be using the right endpoints. You might recall that you could either use the maximum function value or the minimum function value or possibly midpoints, or you have the option of using left endpoints, which is like the left x value of your subintervals, or the right endpoints, which are the right x values of each subinterval. And so here we're using right endpoints. You can see in the picture that we have exactly what we were looking at in packet 22, so this x squared curve from x equals 0 to x equals 1. But now our interval is chopped up into a bunch of subintervals. Now we can't really draw exactly what n looks like because we don't know how many rectangles or n rectangles because we don't know how many n is. We're just drawing a bunch of rectangles just to represent that we're chopping this up into a bunch of subintervals. So we have a certain number of rectangles, and we're using the right endpoint. So notice on each of these subintervals, we're using the right x value to plug into the function to get the height of the rectangle. But what's the width of these rectangles? Let's see if we can figure that out. The rectangle widths well, we can get the rectangle widths by taking the interval length, which is 1. You can get that by calculating 1 minus 0, and divide it by the number of subintervals that we want, or in other words, the number of rectangles. In this case, it's just n. So the rectangle widths are 1 over n. What that means is that this first x value on the right side of that first subinterval is 1 over n. The next x value would be 2 over n, right? Add another 1 over n to get 2 over n. Add another 1 over n, and you get 3 over n, and 4 over n, and so on. The last x value is 1, which you can also write as n over n, right? If you keep doing this for n subintervals or n rectangles, the last rectangle is going to be n over n, which is just 1. Okay, so with that in mind, let's try to calculate the areas of each of these rectangles and see if we can add them up to something. Well, first off, the height of each of these rectangles is given by the function values at each of these x values. On that first subinterval, we're using the right x value, which is 1 over n. We're plugging that into the function to get the height of that first rectangle, and then if we multiply that by the width of that first rectangle, which is 1 over n, then that gives us the area of that first rectangle. Again, doing exactly the same work as in packet 22, but just generalized because we don't know how many rectangles we have exactly. On the second subinterval, if we're using the right x value to plug in, that's going to be 2 over n. Plug that into the function to get the height of that second rectangle. So f of 2 over n represents the height, or the y value, of that second rectangle. Multiply that by the width of that second rectangle. And you can keep doing this for all of the rectangles, where the last one will be f of n over n times 1 over n. Kind of ran out of room there. Well, the function in this case is x squared, so we can plug in 1 over n into that x squared function. Here's what it'll look like. There we go. But we just learned some handy notation to write summations in a much more compact form. So we just have to figure out what the pattern is from term to term. Well, the only thing that's changing here is the top of that first fraction in each of the factors, each of the terms. So we have a 1, a 2, a 3, 4, 5, 6, 7, 8, all the way up to n. So we can write this as the sum as I goes from 1 to n of I over n squared times 1 over n. Right, the n's are not changing on the bottoms here. It's only, and the squares are not changing. It's only that top number in each of those first fractions. That's going 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to n. And so if we write this as a summation, I going from 1 to n, this would be a short version of this summation. So that's good. Now we don't have to write as much, for one thing. And it also means we can use our properties. It helps us to be able to use the properties that we learned about. For example, well, first off, let's just try to simplify. So we can square the I. I want to write that off to the side here. Then we can square the n on the bottom, and that will multiply to this n on the bottom and give us 1 over n cubed. But as we mentioned, the only thing that's changing here is the I. The 1 over n cubed is not changing from term to term. It's a constant from term to term. So we can factor out that constant from the whole summation. If every term has a 2 in it, you can factor out a 2 from every term. If every term has a 1 over n cubed in it, you can factor out a 1 over n cubed from each of the terms. The key is that the n is not changing from term to term. The I is changing. The I, and which is part of the I squared, that's changing. It's different for every term. But the 1 over n cubed, it's the same thing for every term. 1 over n cubed, in other words, does not depend on I, and therefore we can factor it out of the sigma notation. Well, this is great because we have a formula for the sum of the first n numbers. The sum of the first n square numbers. So this is like 1 squared plus 2 squared plus 3 squared all the way up to n squared. We have a formula for that. It goes something like this. I'll write it in brackets. N times n plus 1 times 2n plus 1 over 6. That's our formula for the sum of the first n squares. Let's try to simplify this a little bit. We can distribute across the top. We'll get something like, if we multiply this out, we'll get 2n squared plus 3n plus 1. Then if you distribute the n in, you get 2n cubed plus 3n squared plus 1 plus n over 6n cubed. So what we've done is we've created a formula that, given any value of n, it's going to compute the approximated area under the curve using n rectangles. So this gives us an estimation of the area under the curve. I'll be more specific. I'll write the area under f of x equals x squared from x equals 0 to x equals 1 using n rectangles and right endpoints. Let's get to the really interesting part, which is to take this estimation and see what happens when n gets larger and larger and larger. In other words, use more rectangles that are going to be skinnier and are going to more tightly fit the area under the curve. So in other words, we're going to take the limit as n approaches infinity of that expression. Well, here you've got an infinity over an infinity situation. The top numbers are going to infinity, the bottom numbers are going to infinity. We could use L'Hopital if we wanted to, but let's go ahead and use that one other trick that we learned about, where you take the top and the bottom and you divide by the leading term of the bottom. So you have something like 2 plus 3 over n plus, we'll have 1 over n squared over 6. Another way you could do it is just divide each of these terms by 6n cubed, and that would work as well. The main thing is here, all those little fractions go to 0, so you just get 2 over 6, which is 1/3. And 1/3 is the answer to the question that we first posed in packet 22. This is the true area under x squared from x equals 0 to x equals 1. It's amazing that it turns out to be a fraction. You wouldn't think, like, a parabola is curvy. How could that give us an exact area of 1/3? But it's true. The area under that curve, under that parabola from x equals 0 to x equals 1 is 1/3. And we know it's true because we used these rectangles to approximate the area, but we used more and more and more of them out to infinity. And so then we approached exactly what the true area under the curve was. So that's pretty cool. That's the use of calculus to help us figure out a problem that before we didn't have a formula for. And now we do. Now we know exactly what the area under this parabola is from 0 to 1. Thanks for watching. See you in the next video.